We're going to be hearing from Dr. Gabrielle Barame, who is a postdoc in the Stevens Lab at the University of California, Berkeley. Gabrielle received her PhD in environmental engineering from UC Berkeley and also earned a BA in the applied mathematics at Whitman College. Her current research focuses on the interactions between wildfire, land cover, and water in the Sierra Nevadas. And since 2013, she's been using a combination of fieldwork, remote sensing, and hydrological modeling to explore how managing natural wildfire and landscapes can improve water resources and forest health. This work is focused in Yosemite and Kings Canyon National Parks, and that's what we're going to be learning about today. So with that, take it away, Gabrielle.
Yeah. All right, thank you very much, Stacy. As Stacy said, I'm going to be talking about this project that I've been working on for over 4 years now. The results I'll be showing today are all from Yosemite because that's where we have the most data and analysis. But if you would like to ask some other questions, we do have some work in Kings Canyon National Park as well. And a lot of this, I think, is relevant to the Sierras and to other mountain watersheds. So we're going to be approaching this question of how restoring wildfire to the Sierra Nevada affects its water resources from a variety of perspectives. First, I'll just give you a little bit of background about fire in our Western Mountains, although a lot of you probably know about that quite a bit. We'll talk about how in this watershed we have interactions between fire, land cover, and the water resources. I'll be talking more specifically about the Illilouette Creek Basin, our main study site, and its unusual fire history, how that fire history has affected its landscape, and how those landscape changes in turn are altering the stream flow and the soil moisture. These landscape changes are also creating a lot of really interesting microclimate effects that we'll be discussing. And we can use hydrologic models to look at how these effects might be changing the water balance more specifically. And lastly, I'll look at some observations we have of how these wildfires seem to actually be affecting the forest health on the ground. Sorry, there we go. So the main thing to keep in mind as the background for this whole talk is that we're talking about landscapes that evolved with frequent wildfire for thousands of years. Before 1800, according to fire scars, it's believed that there were many times more acres burned every year in the forested areas of California than we've had recently. Even though in recent years we've had an increase in the area that have been burned by wildfires, we're still nowhere close to what it looked like historically. There used to be relatively frequent, probably mixed severity fires, and that's what these landscapes adapted to. But starting in the late 1800s, fire suppression became the norm in California and pretty much throughout the western United States. And what that does is it completely changes the nature of the landscape. You get these really dense homogeneous forests, and you also get dense fuel buildup. And so what a lot of people, I think about when they think of fire in California nowadays is something like this. Oops. Sorry about that. These dense forests, and you get a large fire that comes through this high fuel load, even though it's meant to be suppressed. Sometimes fire gets out of control and then quickly gets to the point where you can't stop it. You get things like the rim fire, where you have just acres and acres, all you can see for miles, that everything alive has been burned. And the hydrologic effects of this kind of large, high severity, infrequent fire are actually pretty well understood. A lot of people have looked at whole hillsides that burn down, and then you get increased stream flow, and you can either get increased or decreased groundwater storage. But often the increased stream flow comes with poor water quality and large floods because you don't have the vegetation to hold the water back. So even though it's an increase in stream flow, it's generally viewed as a negative hydrologic outcome when you have these big high severity fires. But that's not the kind of thing I'm going to be talking about today. I'm going to be focusing on, instead, you have a fire regime that looks more like what we think existed in this landscape historically, where you have a higher number of fires, but they're smaller and they're not all high severity. And you get landscapes like what you see on the bottom right, where you have sort of a mix of different age classes of vegetation, mix of types of vegetation. And the effect of these kind of mixed severity, frequent fires on a landscape are not really well understood in terms of how they affect the water balance, mostly because there aren't a lot of places where we can study this kind of thing. So where I am studying it is the Illilouette Creek Basin, which is a really unique place in Yosemite National Park. And the main thing that makes it unique is that it's actually had a fairly natural fire regime since the early 1970s. It was suppressed for years, starting in the 1800s, just like all of California. But then in the 1970s, the managers started thinking that maybe this fire suppression wasn't the only way to go, and they decided to see what happened if they allowed the lightning-ignited fires to burn naturally. And so now the fire return interval in Illilouette Creek watershed is actually very similar to what it was prior to 1800, according to fire scars. There's only one other place in California that has had its fire regime restored for this length of time, but Illilouette Creek is the only place where we actually have long-term streamflow data as well. So for answering the hydrologic questions, this is really the one place that we can study. And the, see right here is the Happy Isles gauge, which is actually just downstream of Illilouette Creek on the Merced River. And that's where we have our long-term streamflow records. So using this combination of streamflow records and the many frequent recurring mixed severity fires that have happened in this landscape, we can answer questions such as how do these fairly natural fires change the stream flow, the summer soil moisture, which sustains plant life, and how does it affect how this watershed responds to drought? So basically distilling all that, my main question is, how do fire, plants, and water interact in this landscape? And you might think that we've basically answered this question in the field of ecohydrology, but it actually gets kind of complicated because there's a lot of competing effects when you remove plants. So let's take a landscape like this one where fire has come through. You have areas of dense forest, areas of open grassland. How do we think that the balance of water inputs and outputs is going to change in these different places? And so the way I look at a landscape like this is, instead of seeing all these trees and mountains, I see a series of fluxes and stores of water. And so some of these competing effects I'm talking about are, for example, so you have solar radiation and precipitation coming in at the top of the watershed, but they get divided up in different ways. In the dense forests, you're going to have decreased solar radiation hitting the ground, and so that's going to reduce the amount of precipitation that leaves as evaporation. You also have more trees in the, however, that use more water, so you're going to increase the amount of transpiration that's taking water out of this landscape in this area where you have dense trees. And also you have interception that's changing the amount of precipitation that's reaching the ground in the first place. And so the balance between all of these arrows is going to determine how much of your water goes into storage, how much leaves as stream flow, how much is infiltrating deep down underground. And so the main point here is you have these competing effects. If you remove trees due to fire, you might increase the amount of precipitation reaching the ground and reduce the amount of transpiration, which you would think would increase stream flow and storage, but you're also increasing the amount of evaporation because you have higher levels of solar radiation, so that could actually decrease the amount of water that you have available for storage and stream flow. So which of these factors wins out? And so before I go into what we found in terms of the hydrology, I'm going to talk more about the fire history of the Illilouette Creek Basin. So this is a map that, sorry, used to be a video, but technical difficulties won't be able to see it. But the main idea here is you can see all of the fires that have occurred inside Illilouette Creek Basin since 1970, and the newer fires are shown in red, the older fires in blue. And we like to refer to this as a jigsaw puzzle because the new fires are generally not burning over places that burned recently. So these fires are exhibiting self-limiting effect, which is really important when you think about fire risk, and we don't want these large high-severity fires that cover too much area. The fires really are keeping themselves in check. And this jigsaw puzzle of fires creates a mosaic of land cover. What we've done here is we took aerial photos from many different years over the watershed, and we used those to create fairly simple vegetation maps. And you can see that the landscape has really changed dramatically, mostly from these fires. In the upper left, you can see in 1969, 1970, when there was still fire suppression going on, it was pretty much just one big forest everywhere that wasn't exposed rock. A few little patches of meadows and shrubs, but not much. But once you start introducing fire, advancing into the 80s, the 90s, and more recent years, you see it becomes much more heterogeneous, spatially variable landscape. You get big areas of meadows open up, new shrubs, and it's not just that one thick carpet of trees like we used to have. You're zooming in on some areas so you can get a better idea of the kind of variability that's getting added in. At the top, you can see there were a few sparse meadows and shrub areas that then expanded following some spots of high severity fire. And the bottom two pieces, that's a zoom in on a different area where you can see it was pretty much just one solid forest back in 1969 when it was still fire suppressed. But then after several fires moved through this area, you get this much more diverse landscape. There's pockets of open areas in the trees. You have dense meadows, which include wetlands, shown in orange. You even have a big aspen stand in pink that appears. And so you can just imagine ecologically, this is creating a lot more different types of habitat. And also the fact that you have these dense meadows appearing suggests that there's enough water available to sustain those. This is just a graph to give you another idea of how much the landscape has changed. You can see conifer in green steadily decreasing, shrub areas increasing slightly, but mostly sparse meadows and dense meadows increasing. And even though the dense meadows don't increase by a very large amount in terms of square kilometers, we have over 3 times more dense meadows now than we had in 1969, which means a huge amount of habitat for places that need that kind of area to survive. Another way we can look at changes in land cover, instead of just saying that it looks more variable, we can actually calculate landscape indices. So don't worry too much about how this is calculated, but basically these are the Shannon's Evenness Index and the Simpson's Evenness Index are 2 different ways of measuring how heterogeneous a landscape is. Both of them go from 0 if you just had one type of vegetation covering the whole landscape, to 1 if you had all the different types of vegetation evenly, randomly distributed across the landscape. And you can see that the index goes up from year to year according to our vegetation maps. And so this actually gives us a measure of how much more variable the landscape is getting. And an interesting thing to note is that it's not leveling off. After 40 years of fire, the variation in the landscape keeps increasing. And so it'll be interesting to see in the future decades whether this reaches some sort of dynamic equilibrium or if it's just going to keep changing, if it's adapting to a new state. Can't really tell at this point what's going on. And here's just a nice picture I like to include to show what this kind of variability looks like on the ground. You can see in this one area we have all these forbs growing that require a lot of water. So it looks like they're able to get it. They also have sunlight because this forested area has burned and now it's opened up more. But nearby you also have some dense forest cover, so a lot of the large old trees are still surviving. You have a little bit of conifer recruitment showing that this area is very dynamic. Okay, so that's what's happening on the landscape in the Illilouette Basin. So now let's get back to the hydrologic questions. One way I mentioned that we looked at the hydrology in this basin and how it may have changed over time is by taking the advantage of the fact that we have very long-term streamflow records from the beginning of the 20th century on the upper Merced River, which includes Illilouette Basin, as well as in some other nearby watersheds. So what we did is we looked at the upper Merced, right here, which is gauged at Happy Isles in Yosemite. And all of these yellow outlines show places where there have been fires since 1972, which is when fire suppression ended in the Illilouette. And we compared this watershed to 3 different control watersheds. And these are controls because they're at similar elevation range, have similar types of land cover, but they have had little to no fire activity over the last 100 years. And the way we decided to compare them was using the runoff ratio, which is the ratio of streamflow, annual streamflow, to the total amount of water that came in as precipitation that year. And so if we're getting more streamflow because we've removed all these trees, which is reducing interception and transpiration, then we would expect the runoff ratio to increase in the upper Merced watershed in recent years compared to prior to the 1970s when it was fire suppressed. So when we did that, we saw that the runoff ratio wasn't changing between the fire suppressed and this active burning period. No significant change. But that doesn't mean that the fires aren't affecting the hydrology, because when we look at our 3 control watersheds, we actually see a significant decrease in the runoff ratio between the pre-1973 and post-1973 periods. And so this decrease could be due to climate, maybe changes on the ratio of rain and snow. But what's important is we would expect the upper Merced watershed to behave like these 3 control watersheds and have a decrease in the amount of streamflow it's generating in recent years, but instead it's staying steady. So that might mean that all of the fires in this watershed are actually increasing the amount of streamflow compared to what we might expect. Another way we look at the hydrologic effects of the wildfires in Illilouette is by soil moisture measurements. We've taken literally thousands of measurements throughout the watershed over the last 3 summers, looking at places with different fire histories, different types of vegetation cover, different topography. And we found that there is definitely a relationship between the surface soil moisture and the land cover. So this figure is just showing a summary of all the measurements we've made and the average soil moisture in terms of the percent water content in the soil under different types of vegetation. So you can see conifer and shrubs fairly similar, even in places that were conifer and then burned and became shrubs. The sparsely vegetated areas are fairly dry. The wettest places are persistent meadows that were meadows in the 70s and prior to that and are still meadows today. And then another place where we have very high soil moisture, but not quite as high, is places that were conifer forests, and after fire, they transitioned to being a dense meadow. And so that's very important because that conifer forests on average have lower soil moisture. So it's likely that these places were drier when they were conifer forests, and now they've become a dense meadow, meaning they have higher soil moisture than they had before, which can be very important. These measurements are all taken during the summer. The soil moisture is what's sustaining all of the plant life in this watershed because there's very little precipitation during the summer. And besides looking at it qualitatively this way, we can actually fit some models to all of the data that we have and allow us to estimate what soil moisture looks like across the entire watershed. So on the left here, we have the Illilouette Creek Basin and our modeled soil moisture over the entire area so white are places that are just exposed bedrock. And so you can see in blue are places generally where we have meadows and wetlands, where we expect there to be very high soil moisture, and then light brown places where it's very dry. On the right, we have a slightly more complicated map. This is what we believe is the change in soil moisture from 1970 to recent years. And this doesn't take into account any climate or changes in the amount of precipitation, anything like that. It's just saying all other things being equal, given the types of vegetation change and changes in the fire history that we've seen from 1970 to 2015, what do we think is the associated change in soil moisture? So you can see the dark blue places are areas where we think there's been a large increase in soil moisture. And I see in the legend here, it's VWC, volumetric water content. So when you see VWC, just read that as soil moisture. And you can see there's a lot of areas that are blue showing that we expect that there has been an increase in soil moisture due to the fire activity and related changes in vegetation cover. But it's not a completely straightforward story. Like I said, sometimes you might have an increase in evaporation from the soil or losses of water in different ways from removing vegetation. So you can have some places shown in orange where you have a decrease in soil moisture due to the fire activity. Here's just another look at those changes in soil moisture. I decided to focus just on 3 different types of vegetation you might see. So each of these dots on the graph is a different location within the watershed, and its soil moisture in 1970 along the x-axis compared to the modeled soil moisture in 2014 along the y-axis. So you can see in places that were conifer in 2017, were conifer in 1970, and were still conifer in 2014, you don't get a big change. The values basically fall along the 1-to-1 line. Same thing in places that have been dense meadows, likely wetlands, during this entire period. But where you get the big changes in places that were conifer in 1970, but now they are covered by dense meadow vegetation. And you can see a lot of these places were relatively wet conifer sites in 1970, but then they got a huge increase in moisture when they transitioned to dense meadow following fire. So there's a combination of impacts going on between the topography as well as the type of vegetation that grew in that determines whether you're going to get an increase in soil moisture or not. Another way that we've looked at the changes in hydrology here is by putting up weather stations to examine the microclimate in different places. So in Illilouette Basin, we have 3 weather stations set up in areas that are just a few 100 meters away from each other, but they are very different vegetation cover. All 3 of these places burned in 2004. 2 of them are high severity, one's transitioned to a shrubland, one is now a wetland. And then the 3rd site, although it did burn, it was low severity, so it's still very dense conifer forest surrounding that weather station. And you can see there's very different soil moisture profiles going on. Our weather stations include varied soil moisture probes, and so you can see the water content of the soil in the meadow or wetland site stays pretty high throughout the year. Under the shrub and forest sites, the soil moisture stays lower, but the timing of those moisture changes is somewhat different. And a lot of that seems to be attributable to the snowpack. So these are some of the most dramatic differences we see between these sites is with our time-lapse cameras that we set up to capture the depth of snow over time. So in this graph, this is showing the winter of 2015 to 2016. We have data from this past winter, but haven't finished analyzing it yet. So you can see in the meadow or the wetland site, the snowpack over time, it gets to a higher peak than in the other sites, and also the snow stays on the ground a lot longer. Whereas if you look at under the trees, it starts out similar at the beginning of the winter, but then the peak snowpack is nowhere near as high as in the other two sites, and the snow melts away months earlier than in the other sites. And this can be due to a combination of factors, partially from the trees just emitting radiation that melts the snow, like the effect that you've seen with tree wells if you go skiing. And also there's more interception of snow in the dense canopy. Another way to look at that is we calculated just the percent snow cover on the ground. So it's just the amount of ground that is covered by snow at any depth. So you can see in the meadow site, it's pretty much covered the entire winter, and then you get very fast loss in the beginning of the spring. If you look at the shrub site, it's very similar, but it starts melting away a little sooner, likely because it's a little higher up on the hill. You have the sun hitting that shrub site a little bit more as you get into spring, melts things away faster. And then if you look at the forested site, just completely different. There's a very short period of the winter when the whole ground is covered by snow, and then you have a few periods getting into the spring where it snows and it's briefly covered, but then it melts away very quickly. So you can imagine that if the entire watershed basically used to be forested, then we can expect that snow used to melt away a lot faster than it does now in some of these new sites that have been opened up thanks to fire. And I mentioned that some of these snowpack differences are likely due to temperature. We can actually measure some of the temperature differences between the sites thanks to our weather stations again. So these box plots are just showing the median and range of the differences in temperatures between our forested site and our shrubland site. And you can see that in the nighttime, you usually have not much, but slightly warmer temperatures in the forested site compared to the shrub site, whereas during the day you have warmer temperatures in the shrub site, which you might expect because it's being hit by more sun. But these nighttime temperatures are really important for keeping that snow on the ground, especially in these elevations around 7,000 feet. We're sort of at the edge of the rain-snow transition, and it's not below freezing very often. So if you're warmer by just a few degrees, you're going to lose that snowpack. And the dense forest cover does seem to be increasing those nighttime temperatures by the threshold amount. So those are all different observations that we have. Now I'm going to talk a little bit about what we've been doing with a hydrologic model called RHESSys, the Regional Hydroecologic Simulation System. And so, of course, when we're using observations, there's always a lot of variables that we can't control for. The weather is different every year, especially in the Sierras. But using a model, we can control for things like the weather or anything else that we want. And so we can get a better idea of how much of the changes that we're seeing can really directly be attributed to the fires rather than to some other effect that we can't observe as well. So I'm going to show a series of graphs here. Let me just explain what you're seeing. So the vertical orange lines are showing the years when we had the largest fires in the Illilouette Basin. And then the black line is showing our median modeled change in a given hydrologic variable between two different versions of the model. In one version of the model, I just started running it in 1970, and then I didn't include any fires in the model. I just pretended the vegetation stayed the same, that homogeneous forest across pretty much the whole watershed for the entire time period. Then I ran a different version of the model where I included the effects of the fire, where within the model, we removed vegetation in places where it was removed in real life and let that vegetation grow back with whatever the new vegetation type was. So all of these graphs, you're not seeing the actual amount of stream flow or soil moisture or anything like that. You're seeing the difference between these two model versions. And then the dotted lines show our 95% confidence interval. So on the left, you can see the difference in stream flow. And you can see there's not a lot of confidence in this one. Our confidence interval includes 0, which would be no change. between the model that ignores fire and the model that includes fire. But you can see there are some years, especially after this large fire that happened in 2004, where you do get a big increase in the stream flow, but then that increase seems to drop back down a bit. A place where you do see significant changes are in our soil water storage. You can see in 1970s, this is before the fires start. There's no difference between the models, and then you start adding fires in, and you get this slow, steady increase in soil moisture, and then you have these bigger fires in 2001, 2004. You get big jumps in the soil water storage, and then that storage seems to stay higher right up to the present day. So those changes in stream flow and especially in soil water storage are due to a lot of different sub-factors that we'll look at now. One thing I talked about that might be important is evaporation from the soil, which can actually increase in places where you have fire because more solar radiation is reaching the ground. But you can see in this graph on the left that there's not a huge impact of these fires according to the model on the soil evaporation. Some years you have less, some years you have more. Recent years when we've opened up a lot of new sparse meadows, you seem to have more soil evaporation, which makes sense. You get a much bigger change in transpiration. So that's water that's being used by plants. So you can see that pretty much every year since fires were reintroduced to this watershed, you get decreases in the plant water use or transpiration within this watershed. And the difference is starting to get closer to zero here at the end when there hasn't been a fire for about 10 years, but still it's an overall decrease in the plant water use. And so a lot of that plant water is probably going into this increase in soil water storage that we saw. And so that can sustain those plants throughout the summer. Another way we can look at how well the soil water is sustaining vegetation is looking at the climatic water deficit. So that's basically a measure of how much water plants need to fulfill all their functions versus how much they're getting. And so we see this decrease in climatic water deficit over time, especially in recent years, which just basically means that the plants are less water stressed according to the model. And a lot of that extra water might also be coming from increases in the snowpack, like we saw at our weather stations. The model also shows an increase in snowpack, especially in more recent years. So on the right, we don't have good measures of the uncertainty in this variable, but you can see it is a pretty complicated question. Some years you get increase in snowpack, some years a decrease, but in all of our recent years, you can see that the peak snowpack is modeled to be much higher in the model, which includes fire, compared to the model which leaves fire out. And that's especially important because this includes the last few drought years that we've had when saving snowpack is really important. Now, there's a lot of spatial variability in those snowpack model results, so I wanted to pull some of that out to show you. Here's an example snapshot from May 2011. The model includes the entire Upper Merced watershed, but here I'm just looking at Illilouette Creek Basin because that's where we have the most changes. And so you can see areas in blue are places that, including fire in the model, gives you an increase in the snowpack. Places in brown are places where, including fire in the model, decreases the modeled snowpack. So you can see not always a straightforward story. In some of our higher elevations, you seem to be increasing the spring snowpack in this model example, but in other places you're decreasing the snowpack. So this is an example from May of 2011. Let's compare it to May of 2015, which was a drought year. And now you can see there aren't as many places that are different, but pretty much everywhere where you see a change between fire and no fire, you've increased the snowpack. And so that's extremely important that, according to the model, in this severe drought year, we have increased the snowpack pretty much everywhere inside of the basin. And it's even more dramatic if instead of looking at May, we look at earlier in February when there was more snow on the ground, still pretty much everywhere during this drought year, you've increased the amount of snow that's on the ground by allowing fires to burn in this watershed. So those are a lot of things that we look at that we think are going to be important to the watershed and how they appear to have changed. But can we actually see the effects of increasing the fire frequency in this watershed on the vegetation? Can we actually see a response in how healthy this watershed is? So one way we decided to explore that question is using the Forest Service aerial surveys of tree mortality that are conducted every summer. It's a really great really great data set where basically every summer they fly across all of California and they map where they see tree mortality based on where they see red pine needles, like in this photograph. And the 2014 and 2015 had really unusually high drought-related mortality throughout the Sierra Nevada. So we decided to see whether the Illilouette Creek Basin, which we think has this increased soil moisture and increased stream flow, is better withstanding the drought than some of the other areas in the Sierras. So we mapped the areas of tree mortality, which you can see here as these blobs of solid colors. And we mapped the most recent fires, and then also the Illilouette Creek Basin is shown here with the blue outline. And you can see there are some places in this region that have really high tree mortality, but they're outside of the basin for the most part. And they're also outside of the burn areas overall. Like you can see here, there's one area outside of the Illilouette Creek Basin that had a fire a few years ago. And you can see all of these patches of mortality nearby that seem to stop right adjacent to that burned area. And I'm sure some of you are thinking, well, of course, there's no drought-related tree mortality within the burn areas. All the trees burned down, so there's no trees left to be killed by the drought. But if you actually look closely within these burn areas, there are still a lot of live trees that could be being affected by bark beetle or other drought-related stressors, but they seem to be surviving it just fine. To take a closer look at all of this, we looked at control watersheds just like we did with streamflow, but now we added a few controls that are down closer to Illilouette Creek Basin, shown here and here. And we calculated the number of dead trees mapped by the Forest Service divided by the forested area within each of these watersheds. And the Illilouette Creek Basin had the lowest number of drought-killed trees per forested acre of all of these watersheds. In some of the adjacent watersheds, you had 50 times more dead trees per acre in 2015. So of course, some of this could be coincidence, could be due to other factors, but it looks like the forests within Illilouette Creek Basin have been healthier throughout this recent drought than they are in places that are nearby, so are supposedly experiencing similar climate. And that's everything I have for you today. So in conclusion, this is a landscape that has changed very dramatically, is more heterogeneous, but is still in transition from its fire suppressed state. We've seen that there's a lot of spatial variability in terms of responses to fire, both in terms of the type of vegetation that grows back and in whether soil moisture or snowpack is altered. Overall, the fire appears to be increasing stream flow from this watershed, as well as increasing soil moisture and increasing the drought resilience. And to get more specific, the drought resilience of this watershed is demonstrated by the fact that the fires are self-limiting. So even if you have hot conditions conducive to a fire, the fire likely won't get too great an extent. You have increased stream flow and soil moisture, which is very important for sustaining an area through a drought. The landscape is more diverse, meaning there's more pockets of places that different types of plants and animals could survive during difficult times. You have deeper, more persistent snowpack in places that have burned compared to unburned areas. And we also have observed a very low disease or drought-related tree mortality within this watershed. With that, I'd like to thank you for listening. Also thank our funders and all the many, many field hands that we've had out there making this project possible. And I'll go ahead and take any questions.
All right, great. So we're going to go through these one at a time here. 1 second. Okay, so the first question is, are there records of landscape types prior to the start of fire suppression?
Yeah, that's a good question. We do have some maps from the 1930s, but we don't have a good idea of exactly how accurate they are. And then there's some other maps here and there of smaller areas, but the Illilouette Creek Basin wasn't a place that was really important for farming or forestry, so it didn't get looked at too carefully. So we have an idea of what the landscape probably looked like, but we don't have any really reliable, solid information.
Okay, so the next ones are a little bit similar. It's some other information about what's happening in the Illilouette Basin. So what kind of forest type is it? Is it mostly comprised of ponderosa, Jeffrey, red fir? And then could the ability of fires be so self-limiting in the Illilouette because of the amount of bare rock and granite? So kind of a combo question there if you want to take it away.
Yeah, sure. So the forest is mixed conifer. You have Jeffrey pine, also red and white fir, a lot of ponderosa pine, a little bit of sugar pine. That's pretty much it. And the shrub areas, I can't remember if I mentioned, are mostly Ceanothus, cordialatus, whitethorn ceanothus. And the definitely part of why the Illilouette Creek Basin was chosen for this type of land management, where fires are allowed to burn more frequently than others, is because of the large amount of bare rock and granite. Most of the watershed is ringed by these large granite peaks. So it's difficult for a fire that begins within the watershed to spread into another part of the park. So that's definitely part of the self-limiting nature, but it's not the entire story. And Scott Stevens and Brandon Collins have written some great papers looking at how fires interact with each other in this landscape.
Okay, so this is kind of a follow-up to that one. And it's not quite typed out all the way, but so if it's, if the fires are self-limiting in this area, is it that can you replicate this kind of fire management in other parts of the Sierra Nevadas?
I believe that you can. I know, and of course, everywhere is site-specific. You can't just take everything we've learned from the Illilouette and plop it down on any watershed in the Sierras, and it'll definitely be exactly the same. That's just not how real life works. But and I know a lot of people are concerned that if you try and just let fires back into a landscape after it's been fire suppressed for a long time, then it's just going to give you a high severity fire and it's not going to give you this type of mosaic. But the Illilouette shows that you really can get a return to these mixed severity regimes even when you've had a century of suppression, just like the Illilouette Creek Basin has. So of course, now the newest fires are impacted by the fires before them and have this self-limiting nature, but some of the first fires occurred in a very fire-suppressed landscape, and they still seem to have achieved a lot of the resource management goals. So I guess to summarize, of course, you would definitely have to be careful trying to reintroduce fire into a new landscape where you might not have the self-limiting effect, but you probably could develop the self-limiting effect over not too long a period of time.
Okay. Another one is, we're going a little bit more on the hydrological side here. Are meadows, shrubs, that kind of combination, or are trees better at sustaining late-term summer flows?
Well, you definitely seem to observe more late summer flows within the meadows, but there's a bit of a chicken and the egg question going on. Do you have meadows because they're in locations where you have sustained summer flows that are able to feed the meadows, or is the meadow vegetation itself more conducive to allowing these late summer flows to persist? And there definitely is some interaction with meadows. For example, that you get more organic soil under a meadow, and that organic soil retains water longer. And it looks like in our meadow site where we put the weather station, you've got some little microclimate changes that are helping to keep the snowpack there longer. And so keeping that snowpack longer helps to feed the soil with water more slowly. And so that that soil is going to keep its water longer and sustain those late flows. So the short answer is meadows are the best, but it's complicated.
As many things in science tend to be. Okay, thanks for that answer. We'll take one more here, which is you showed modeled soil moisture changes when transitioning from conifers to meadow, for example. Can you describe that model a little? Was it based on correlating soil moisture with land cover types?
Yes, so I imagine we're talking about, get back there. I assume everyone else can still see these slides also. Here we go. So I assume we're talking about this model. And so it's a statistical model. It's actually a random forest model for those who are familiar with that. And you basically, the variables that you give it are slope, aspect, elevation, times burned, time since fire, and vegetation cover. So a lot of it is based on correlating the soil moisture with the land cover, but it also takes into account the local topography and also the fire history. Does that answer your question, or did you want more details than that?
We'll let them type if they need to follow up, and we'll switch a little bit here. So is there an estimated time frame of when the burned areas will transition back to a full conifer forest?
Yeah, it's a good question. Some places have definitely transitioned back to forest already after burning in the 70s or 80s, but obviously it's a much younger forest with shorter trees. And part of the question really is, would all of this place return to a conifer forest if fires were stopped today, or would some of it just transition to shrub and stay that way for years? Or transition to a more sparsely vegetated landscape? It's really a more complicated question because the climate appears to be in transition. But a short answer would probably be on the order of decades, for sure. The return interval of these fires is about 6 to 8 years. And so that seems to be enough to keep conifer from growing back in certain areas. But in other places it is coming back, or it's transitioning to a different state.
Excellent. Okay. Different perspective here. Has any sort of economic analysis been completed comparing the upfront costs of restoring fire to the Illilouette compared to the long-term costs of managing a suppressed watershed?
Oh, that's a great question. I don't think anyone's done that analysis for the Illilouette specifically. I know there has been a lot of economic discussion about suppressing forests versus just managing them for resource benefit in the Sierras in general. Which I could think of some of those specifically off the top of my head. I know these types of analyses have been done, and a lot of the motivation for trying to increase the number of areas where we're allowing fires to burn is that the costs of fire suppression have been getting so high, especially in recent years. So my understanding is that in general, a lot of managers now are looking at using either prescribed fire or wildfires that are managed like in the Illilouette to sort of reduce the risk of extreme fires in a cheaper way than if you were suppressing large areas or having to deal with things like the rimfire. So there is an idea that this is a cost-saving measure, but I can't give you exact numbers.
I think that might be an excellent place to, oh, wait, one more. We'll do one more, and then we'll call it a day and let people go off for their lunch.
Okay.
So our final question here is, are you thinking climate change will slow the progression of burning areas transitioning back to conifer forests?
Well, I am thinking that. I haven't done any sort of formal analysis on that. I know there are other papers that are looking at areas in the Sierras, especially at slightly lower elevations within the conifer belt, where it does seem to be transitioning to oaks or to shrubs rather than having conifer grow back immediately after fires. So my understanding of this area makes me think that, yes, you are going to slow the transition back to conifer forest because of climate change, because it's getting warmer than a lot of these forests would like. Also, you're getting less snow compared to the amount of rain. But I haven't done any kind of formal analysis or modeling for this area in particular.
And I will say, too, that feel free to contact myself or Gabrielle with follow-up questions about this, or if we can get you in touch with some other resources if you need them. And we'll go ahead and end a little bit early here, but I want to thank everyone for joining us today, and a special thank you to Gabrielle, who did a wonderful job. And I know this work is continuing, so we look forward to knowing more about fire in our watersheds. All right, thanks, everyone.
Thank you, Stacy.
The chairperson has disconnected. The conference will now end.